From last class period's lecture, we talked about why Schrödinger developed it, basically because Paul Debye kind of teased him like you're treating it childishly and you need to have a wave equation if you're going to deal with waves. And in the normal sense, a wave equation is an equation that you use to find the function that describes a wave. And so this equation that Schrödinger found is likewise an equation that allows us to find the function to describe our wave. So the wave is something describing, in most of what we're going to do, like an electron. And that something is part that Schrödinger just didn't know. He found a wave equation. He didn't know what it really meant. And we now have a sense of what it means, so we're going to start with the benefit of that knowledge. But he found this wave equation that then gives you a function. It gives you psi, and that's my version of psi, okay? You'll see different versions of psi, and there's like uppercase and lowercase, and we will use uppercase for the complete psi and lowercase for one of the possible states, and different fonts, so you just kind of have to get used to it. Where was I going with that? Don't remember where I was going with it. Well, anyway, the meaning of psi is an important thing that comes up in just a couple slides. You use this equation to find the wave function, and that wave function psi contains all of the knowledge we have about our system. It's kind of bizarre to me to think that the only thing that really is a variable in this equation, or a variable that changes from one case to another, is the potential energy function V. And yet we can get the complete description of what is happening based on just that potential energy function. And it's all in this convoluted looking wave function that we find based on solving this equation. Now, this equation has a time component because it's dependent on time, and a position component. This is, of course, a one-dimensional version. If you have a three-dimensional, like we do live in three spatial dimensions, you simply change the second derivative to that. That's the, gradient squared. I'm sure there's a name for it by itself, like, I don't know. I can't remember. I'm not going to go out and guess. You guys, well, Indy, you're a math major, right? You know, okay. Oh, it's Chris that's a math major? What do we call that? Okay. Okay, so we'll just be happy and call it that. That is in Cartesian coordinates. And are you guys more comfortable using I hat, j hat, k hat for unit vectors, or what's your preference? X hat, y hat, z hat, I, j, k? So oh, come on. Right, it's a directional derivative. And then when you have the squared, that's equal to that. And so dot product, the I only acts on the I, so it just gives you second derivative x direction plus second derivative y direction plus second derivative. And you guys are very clear on partials versus exact derivatives, right? Or no? Okay. Okay. Just want to make sure, I don't want to talk and have you guys go, yeah, he assumed too much. Like, did you assume my gender? Did you assume my math? Anyway, so this equation is going to be highly important to us. We're going to use it in, well, actually only like 4 or 5 different situations because, hey, we're kind of limited in our abilities at this point. If you want a pro, probably Blake is a pro because I taught a class of particle physics a couple years ago. That's his area specialty, and I discovered, wow, there's a huge amount of quantum in there. But we're going to be doing fairly simple situations. So what is this Greek letter psi? What does it mean? Well, Born's statistical interpretation says that psi mod squared, that's this here. Either way, that means that's not how you actually spell psi. We say psi mod squared for that. It's amplitude squared. Absolute value sign is really what it means. But when you do the absolute value of a complex function, because you know what? There is no rule that our wave function has to be real. It can be complex. It can have real parts and imaginary parts. And so you need to do the complex conjugate times the original function to get the psi mod squared. And while you probably are both very familiar with complex conjugate, the rule is simple. Psi star is equal to psi with all i's becoming minus i's. So that complex conjugate, if I have psi is equal to a e to the minus lambda x e to the I omega t, I chose that only because that's one of the problems I hope to do in today's class, except for with the absolute value sign. If I want to take the complex conjugate of that, the star is called the complex conjugate. And since I don't know what A is, I'm just going to assume that A is complex and put A star. So that means my rule for complex conjugate has to be applied to A as well. E to the minus lambda x, those are both reals. And so there's no change there. But then here I have an I. And so that I is going to become a minus I omega t. Right, so the complex conjugate, the only difference was changing the sign any place I occurs. So in practice, it's really easy to enact. And the reason for that is when you take the complex conjugate times the original function, you're always going to have a real result, no complex anymore. And it tells you the magnitude squared. Of course, you square root it and you get the magnitude. So Born called that the probability density. The probability density because it's the probability per unit something. So traditionally, we are going to find our wave function with variables time and position. It doesn't have to be time and position. We can find a wave function in momentum space, right, in time and momentum. But we're going to find it in time and position traditionally. And so in that case, we're going to have dx for the range within which we're finding the probability of the particle existing. So the complex conjugate squared, or complex conjugate squared, the psi mod squared, is the probability density. You multiply by dx by the little range that we're going to look in, and that gives you the probability. Well, it says right here, probability of being between x and x plus dx. I'm not going to rewrite the entire thing quicker since I already have it typed out. So that's an important thing for us. Quantum mechanics is doing a lot of statistics calculations, and so we're going to talk about probabilities a lot of the time. And so if I want to find the probability of a particle being between A and B, where A and B are some finite difference from each other, remember, dx is infinitesimal. It's a minute range that we're looking at there with dx. If I want to find between A and B, I just add up all of the probabilities between there. So if I have a function that is, well, let's just take the function I made there, the spatial function. So I'll put psi as a function of x comma 0. If I put 0 here, it's just going to be an exponential decay. And let's say I want to find the probability of being between A and B. So here's my psi function. How do I find the probability of being between A and B? That's exactly right, Indy. I integrate the probability density from A to B. So I'm going to find the area under the probability density curve. So this here I wrote psi, the probability density curve. So I'm just going to, I'll change color at least so it has less confusion. So if I do that, if I take psi mod squared there, I've written it out long form, but you know that when you're multiplying exponentials, you can combine them and add. So that's equal to A and A star is A mod squared. So I'll just put that out front. And then I have e to the minus lambda x, e to the I omega t minus I omega t. E to the I omega t minus I omega t does a wonderful thing. That's just e to the 0, which is always 1. And so that goes to 1. This one here, minus lambda x is really quite simple. So that's what I'm going to actually be, that's my probability density. I take that probability density dx, that's really smooth, and integrate from A to B. So what's this going to look like? It's going to look exactly the same, except for your decay has a 2, so it's got a slight different scale for the numbers. So now that I have probability density, I simply want to find the area under here, which Indy perfectly described as probability between A and B is equal to the integral from A to B psi mod squared dx equals integral from A to B. And finally, I just have to do some math. So taking the integral, my understanding is you guys are both real good at math. What math classes are you in? You're both in linear right now, is that right?
Yeah,
They both in linear and differential equations. Well, yeah, I guess it's a math major. I was like, 3? Seriously? Because those are all serious classes. So taking the integral of an exponential, you just divide by the derivative of the exponent. And keep everything else the same. And there we have the probability of it being in that range. Now, of course, we don't have any numbers here. It's hard to make any kind of sense out of this. Did that make sense or not? You can say this probability had better be less than 1, right? It can't have a greater than 1 probability of being in this range. But without having already calculated A, we can't say. So that brings us to first some philosophy and then back to the point. Why is the philosophy here? Well, it's changed over time. You see, I mean, I'm pretty much following the textbook here. It talks about these 3 different viewpoints. Einstein is very famous in being a probability denier. Einstein has a famous quote, "I do not believe that God plays dice with the universe." You guys probably heard that, right? What do you interpret that to mean?
like there's a way of finding things in a specific place. It's not just a probability of it being everywhere.
That's right. Go ahead. Yeah. So he believed in determinism. If we have enough information, we can always determine what's going to happen next. So, Einstein thought of this kind of like we think about chaos theory. With chaos theory, you have a really complicated system, and you have to know the values of your variables out to many, many decimal places to be able to predict very far in the future what's going to happen. But unless you have perfect knowledge of, out to infinite decimal places, after a short amount of time, your predictions become wildly inaccurate so as to be useless. And Einstein thought that's what we were dealing with quantum mechanics, that we just don't have enough information. If we get the information just right, we'll be able to determine exactly what transpires, how a system is going to move. And one thing I always point out with this quote, God does not play dice with the system. You'll see that quoted with inspirational quotes all the time in Christian resources. Well, depending on who asked him and what time of day it was, Einstein was an atheist or an agnostic. He wasn't talking about God like I think of God. He was talking about nature. He was saying that he did not believe that nature was random, that nature was determinist, just as the two of you explained. So that's the realist point of view, says that if you take a measurement of a particle and you find it's at point C, just before you took the measurement, it was there at point C. Because where else could it have been? By just before, I mean an infinitesimal time before. That's the realist point of view. That was Einstein's point of view. Niels Bohr took the position that is now considered orthodox. Since the late 60s, it's the standard position, that the particle didn't have a specific place. And of course, this is where things get really mind-bending. You think about a wave. If I have a wave of light, that wave of light is traveling like this, and I say, where is the wave? How do you identify its position? Right? This picture has position on this axis, and the wave exists throughout the entire range. And so you would have to say, well, the wave is everywhere. Now, you can be more specific. We can make what we call a wave packet. Say, for instance, you're studying femtosecond lasers, short pulses of lasers. What you have is a wave packet. It's flat, and then you have something like this. And so we call it a wave packet because, you have a packet within which a wave exists. You've probably already studied enough to know that you can use Fourier analysis, and you're going to have a range of frequencies present. And with this, we could say, well, within a certain certainty, the position is in here. And so we have a certain uncertainty in position there for the wave packet. And using the Fourier transform, you can also find, uncertainty in the frequency and put those together. It actually is, that's how you get the limit for Heisenberg's uncertainty principle, is looking at a wave packet. So you can have the position for a wave packet, but there's some uncertainty there. And so Bohr says, we don't know the specific place. If we have this packet, we could say it's somewhere within this range, but we still don't know its exact position. And in this case, we know exactly the frequency, but we have no idea what its position is. So here, frequency is exact, position is perfectly unknown. Whereas with the packet, there is a, I could have left the U, uncertainty in both the frequency and the position. But we never have one exact unless the other one we have no idea about. And so that's what Bohr's talking about. The particle has no specific place. It's a wave, and the wave, you can't really define its place. You can get closer and closer until you have a delta function and say, it's right there. But a delta function has an infinite range for the frequencies. And then there's the agnostic point, what's the use? As the textbook says, up until around, I think it's 68 or 69, physicists who were arguing the orthodox, if people were like not buying in, they'd say, what difference does it make anyway? And end the argument. But there are actually experiments that showed in, like I said, late 60s, that this orthodox view has to be the correct one. Now, the textbook says, we'll leave it to the very end to actually discuss that, at the end of the textbook when you could understand it. But the understanding that we have today is that Einstein is wrong. that it's not a lack of knowledge. It is a fundamental property of nature that it's not predictable. In the minute scale, it's not predictable. There is no specific place. The particle could be, anywhere in this packet. If you make a measurement and you find that it's right here, then what you've done is you've taken the particle that was spread out everywhere and forced it to be one place. We call that collapsing the system. And so by making a measurement, you've changed the system. You've changed it from being randomly located to a specific location. This, our textbook has two images. Have you noticed the front and back are not the same image? That's making reference to the Schrödinger's cat. You guys know the whole story of the Schrödinger's cat? Okay, good. Then I can actually start from scratch. Schrödinger's cat is a story to deal with how we understand a superposition state. A superposition state, superpose, means you have multiple states that you put together. Our understanding of quantum physics is that a system is naturally going to be in a superposition of multiple states. So that's kind of like saying you have the hydrogen atom, and we talk about it being the n equals 1 state or the n equals 2 state, and I know we have the other quantum numbers, but it can be in these different states. And if we start with it in one state, over time it's actually going to evolve. So it's like 30% in state 1 and 40% in state 2 and 30% in state 3. And so it's in all of these states at the same time. But there's a probability associated with each state. So it's this probability in this state. It's not if you test it, it's going to be in that state or in all of them. When you test it, it's forced to be in only one. And so the Schrödinger cat, and by the way, I should point out, I always try to pronounce Schrödinger right, and I'm sure I'm wrong. The O umlaut, I asked a German guy, and his last name was Schroeder, so I figured he'd be like keen on it, and he's like, shrugs his shoulders. So the idea is you take a real system and combine it with a quantum system. So that real system is a cage, and in that cage you put your little cat. My cats are pretty non-sophisticated. And you also put in that cage a radioactive sample. So here's my radioactive sample. Okay, I'm never going to get it's magenta at least, radioactive symbol. And this sample has a half-life of, let's say, 1 hour. So what that means is the sample is a quantum system, and the quantum physics says that you start in 100% the undecayed state. It's radioactive. And, I should have said it's one radioactive atom. The sample is one atom. It's a mythical system. And it has, initially at time 0, it's 100% in the undecayed state. And over time, the probability of it being undecayed drops, and the probability of it being decayed rises. And so you can make a graph of the probability of being undecayed starts at 1, here's time, and after 1 hour, it's dropped to, that's a 0.5, it doesn't look like it. It's dropped to 50% undecayed. So it's 50% undecayed, and of course, it's only a 2-state system, it's 50% decayed. So if you do the probability of decay, it's just going to look like that. So they add up to 1. You have in this system a perfect radiation detector. It's completely encompassing your atom, and it's going to detect when it decays perfectly. And when it does, it's going to drop a hammer on a vial of cyanide gas, which for my cases is going to be sitting on an anvil here. So the hammer drops, it hits the vial of cyanide gas, the cat breathes the cyanide gas, boom, it's dead. Now, what is special about this? That's the entirety of the Schrödinger cat. What's special about this is your cat is now tied to a quantum system. So if the radioactive element has decayed, the hammer's dropped, the vial has been broken, the cat has died. And so quantum physics says at 1 hour's time, the cat is 50% probability perfectly alive and 50% probability perfectly dead. But quantum physics doesn't just say that when you test it, it's going to be 50-50. It says that it is at that time living in those two states. So at that time, it's 50% fully dead as a doornail. You know, you could drive nails with it. And it's 50% fully alive. And you think about it, you're like, well, that doesn't make any sense. How can a cat be 50% fully alive and 50% fully dead? Does it feel a little sick? No, it's just 50% alive and 50% dead. And now comes the real, the reason you have the silly jokes about, Schrödinger or whatever in a car. Schrödinger, Heisenberg, and I think it's the psychologist in a car get pulled over, and Heisenberg's driving, and the policeman says, "Do you know how fast you're going?" Heisenberg says, "I have no idea." And the police officer says, "You were going 65 miles an hour." And Heisenberg's like, "Oh, great. Now I have no idea where I am." Because the Heisenberg uncertainty principle, if you know exactly your speed, you have no idea where you are. And then he says, "Can I check your trunk?" And so he says, yeah, he pops the trunk, he goes and looks, and he says, comes back and says, "Do you know that you have a dead cat in there?" And then Schrödinger gets all upset because the dead cat, Anyway, and we won't go with the psychologist part because who cares? It's not physics. So the whole point of the Schrödinger cat idea is when you check to see the cat is either going to be alive or dead. You collapse the system into one state or the other state. And if it's alive, you just start over. If you checked and the cat's alive, you just jump back to the starting point again. And if you check and the cat's dead, well, it's over. But as long as you never check, that cat's never going to die. It might be only 0.00001% alive, but it's fully alive in that 0.0001%. That's what quantum physics says. So this whole Schrödinger cat thing was designed to just show how silly it is to take the orthodox view. And yet quantum physicists said, yeah, that about sums it up. So what I'm saying here is quantum physics is kind of anti-intuitive. We have some things you kind of have to take on faith. Hence you have the famous quotes, if somebody tells you they understand quantum physics, they're lying or they're ignorant. Because it's really mind-bending like that. Okay, now going back to real things. Basic premise here is that when you make a measurement, it's going to collapse from being a whole bunch of different states to this exact state. So you make a measurement, you change the system fundamentally by making the measurement. You either killed that cat or you made it full health. And then the system will progress again afterward. Now, if you want to follow along, pages 5 to 9 is a whole bunch of statistical things to help us understand what we're doing in quantum physics. And so I'm going to go through doing the stuff there on pages 5 to 9 so that you can make sense of it and ask me questions of things that don't make sense. So in quantum physics, we're doing a whole lot of statistics. You notice here I said it's just statistics. It's just really complicated statistics. So we're going to be using ideas like probability, as we've already seen, the most probable state, the median state, the average of squares, standard deviation. We're going to use all those things. So I have here a collection of numbers. This is the same collection that's in the textbook, except for it doesn't put it in tabular form. I don't know why. It seems to make much more sense to me to have it in tabular form. So we have just a bunch of ages. And if I were to ask you, what's the median age? So going to median. How do you identify the median? Yeah, it's the middle one. The median is the middle one. It's the one that, as the textbook says, you have equal probability of measurements being above it as you have below it. And so in this case, because we have a total of 14 people, then we just say, okay, 1, 2, 5, 6, 7. So the seventh one is here, and then we have 7 above. So the median is going to be between 22 and 24. So we'll go with 23. It's between 22 and 24. So there's our median. With the discrete system, I'm actually not sure how you're supposed to treat it, but hey, that's our median. The most probable is pretty simple. Which age is the most likely? If you ask a person, what's your age? Which one are you going to get the most often? 25. So the most probable is 25. That was easy. It's the one that had the highest probability. I can calculate the probabilities real simple. The probability is 1 out of 14, because the sample size is 14. Likewise, 1 out of 14, 3 out of 14, 2 out of 14, 2 out of 14, and 5 out of 14. Probabilities are very simple for this system. Now, what if I want the average? With a system like this, you're probably likely to just add them all up and divide by the number of students, right? But it's a lot quicker to say, let's just do a summation. Let's say the average or mean, average and mean mean the same thing. We have a symbol for the average or mean. So that less than, greater than sign combination means we're finding the mean, and we have a special term for it, expectation value. So that, expectation value of A is how I'd read what I wrote. And we can find the expectation value, or the average or mean, by taking the sum over all possible ages. So I'm going to use J for each age, of the probability of that age multiplied by the age. I'll put a parenthesis instead of a dot there. And then I need to divide it by the sum of the probabilities. What's the sum of my probabilities going to have to add up to? Say it out loud. Yeah. I saw your mouth move, but I didn't hear anything. Maybe you just said it too soft for the mic to pick up. I'm not a good lip reader. And so the bottom is just going to be divided by 1. So it's kind of meaningless for our calculation because it's just divided by 1. And so we go through and we would say, okay, that's equal to 0 times 1 plus 0 times 2, et cetera, because probabilities of any number not shown is 0. And so I'll just get to the ones that aren't 0. 1/14 times 14 plus 1/14 times 15 plus, and of course this quickly gets annoying, 3/14 times 16, 22, 24, 25. When the pen is too close, it won't move, in case you're wondering why I'm sitting here swiping and nothing's happening. That's not a... Okay, that's writing out in gruesome detail how we would find, using the probability and the values, the expectation value. And honestly, I don't feel like calculating. I'm going to open the book because I'm pretty sure it calculates what it is for us there. And so it tells us the expectation value is 21. And so 21 is our expectation value. What are the chances that I do a measurement and I find the person says they're 21? 0, right? So expectation value doesn't mean it's what we're going to find often. In this case, it's not possible to find the expectation value, but it's the average value. So if you do a bunch of measurements, the average is going to be the expectation value. So that's what we mean in quantum mechanics when we say the expectation value. The average value we will get when we take a bunch of measurements. Now there's some, we've got 13 minutes. I'll keep going with this. I obviously want to get past this for today. There's some additional calculations here. Calculating, the probability I've already done. I'll mark that off. The average of the squares. Calculating the average of the squares is not the same as taking the average and squaring it. So just to illustrate that, here we calculated the expectation value for age. Now I'm going to copy this to save us some time. And I'm going to do the same thing, except I'm going to now calculate the expectation value for age squared. So instead of age, it's going to be age squared. Perfect. And so that means I'm going to have the same probabilities, but I have the square on all of the ages. And so if you do that and you do the calculation, it's going to give you a much higher number, which I trust the textbook gave us. I don't see it here in the textbook. I don't feel like doing the calculation. So I'm not. Instead, I'll do the calculation based on a 3 system, a system of 1, 2, and 3. What is the expectation value if they're equal probabilities of 1, 2, and 3? 2, right. Because expectation value, if they're equal probabilities, it's each one's 1/3. So I'd have 1 plus 2 plus 3 is 6, divided by 3, 2. So the expectation value for that 1, 2, 3 system is simply 2. Now what about the expectation value for the squares? So that means I have 1, 4, and 9. That would be the average between 1, 4, and 9 is going to be 14 divided by 3. And so 14 divided by 3 would be the expectation value for, so let's just go over here. So I have 1, 2, and 3 are my values. The value squared is 1, 4, and 9. So this has a total of 6 here, total of 14 there. And so the expectation value of V is equal to 6 over 3 equals 2. The expectation value of V squared is equal to 14 divided by 3 is equal to 4 2/3. And so if I compare these, if I were to take the expectation value of V and square it, that's equal to 4, which is less than the expectation value for V squared. And it's always going to turn out that the expectation value of the square is greater than, hey, look at that. It's really nice to have the greater than sign when you're doing these, than that. So there's a difference between finding the expectation value of the square and squaring the expectation value. Now, the last thing here, which I will skip over, it's going to come back, standard deviation. The deviation is how far a value is from the mean. So I could go through it. I've got the mean is 21. So the deviation for 14 is 7. Deviation for 15 is 6, and so on, right? And you're going to have positive and negative deviations. The average of the deviations, it's going to have to be 0, right? Because the deviation from mean, if you average the deviation from mean, you have as much above and below, and averages to the 0. So nobody calculates the average deviation. That's why we use standard deviation, because average deviation is just 0. You've probably taken enough electricity. No, nobody talks about the average voltage in an AC circuit because the average voltage is 0. So what do they do instead? They square it, find the average of the square, and then take the square root. And that's exactly what the standard deviation is. It's exactly analogous to the RMS voltage. You take the deviation and square the deviations, you sum all the deviations squared, and then you take the square root of that. And I will leave it to you to follow through the, to get to equation 1.12. I was going to do that, but I only have 8 minutes left. And so I'll leave it to you to follow through that math. Just that is an actual important outcome, that the standard deviation is the square root of the difference between the expectation value of the squared minus the square of the expectation value. It's not hard math to follow. Much harder math to follow what's coming above or below. So what's coming below? If we have a continuous system, we still use the same statistical ideas. The same, take the probability times the value and add all of those up. But if it's a continuous system, a summation sign becomes an integral sign. Conveniently enough, the integral sign is basically an S for sum. Sigma is S in Greek. They both are S for sum, basically. So we're going to change from integral, or from summation sign to integral. So up here where I had the sum of j, sum over j of pj, I'm going to have now the expectation value is equal to the integral of the probability density times my variable. So there's the probability density and then the variable. And I put a y instead of an x. I should have put dx. So that's how we do it. But remember, according to the Bohr interpretation, the probability density, okay, that's probability density, yeah. The probability is psi mod squared. And so this is equal to the integral of now I changed the order. I changed the order because that's actually how we solve it for anything. We use an operator here. We'll learn about it later. But that's still psi mod squared is psi star psi. And so we have the psi star psi in there. And then we have our operator, which it turns out the x operator acting on psi gives you x. And then you do the integral. So this is how we find the expectation value for a continuous system, for our quantum mechanics. Next important idea is normalization. As a physicist, I know people don't think of us as normal, hence I try to put this in, we need to be normalized. Normalized has a very simple meaning. What did we talked about this before. What should the sum of all of the probabilities be? 1. And so that's what normalization means. Normalization means that we need to find our wave function so that the sum of probabilities over all space is 1. So what is the sum of probabilities over all space? That is the integral of psi mod squared dx over all space has to be 1. Now, if we look back at our Schrödinger equation, the first slide, notice that psi appears in every term here. So if I multiply psi by any arbitrary complex constant, as long as it's a constant, the derivatives won't affect it, and it'll just be something I can factor out, and the equation remains unchanged. So a wave function that satisfies the Schrödinger equation will still satisfy the Schrödinger equation if I multiply it by any complex number. I say complex because it doesn't have to be real. It doesn't have to be complex either, but it can be purely real, but it could be complex. So I'm going to take any wave function I find, and the first thing I'm going to do is find what constant I need to multiply it by to make it normalized, to make the sum of probabilities come up to 1. That is to say, if I look at the probability of finding my particle in every possible location, I add up those probabilities, it's going to have to be 1. And so we calculate that by doing the integral. And so we call that process normalization. Now, the proof that the solution to the Schrödinger equation remains normalized over time, that it doesn't start normalized and then over time vary away from normalization, is not going to be done in 3 minutes. The proof is shown in the textbook, so I'm going to do the hand-waving explanation for the proof to make sure that it's clear. So if you look at page 13, page 13 we start with saying, okay, what we want to do is check how the probability changes over time with psi. So we're starting with the derivative with respect to time of the integral over all space, so all space going from minus infinity to plus infinity, of the probability density, psi mod squared dx. Now, just to make sure there's no uncertainties, I have psi parenthesis xt. That means psi is a function of position x and time t. And so we're checking to see what this equals. The next step is fundamental, but he even took time to point out you can move that derivative into the integral because it's a derivative with respect to time and the integral is with respect to position. Different variables, you can move it through. But since when you do the integral, you integrate out position, the integral for the probability only gave you a probability as a function of time, hence it was an exact integral or derivative. When you put it in, now your function is both time and position, but we're only doing derivative with respect to time, and so it has to change from an exact to a partial derivative. And I'm going to drop the x and t to save writing. And so that's equivalent. Now the next step is he says, we're checking the Schrödinger equation. So by the Schrödinger equation, if you look at 1.23 and 1.24, 1.23 is the Schrödinger equation, just solving it for the time derivative. And then 1.24 is the complex conjugate of 1.23. So those are using the Schrödinger equation and the complex conjugate of the Schrödinger equation. Equation 1.22 is simply using the product rule on the derivative of psi mod squared. And then you combine equations 1.23 and 1.24, you substitute those into the product rule equation 1.22, and that's what gives you 1.25. Once you're at 1.25, you go back to the original integral equation 1.21. I know, having it explained is not nearly as fun as seeing it done. And you get this, the derivative with respect to time of the integral of psi mod squared, that is the derivative with respect to time of the probability, is equal to I h bar. Did I last class period talk about h bar?
Yeah.
Okay, good. I know I had planned to and wrote out some stuff on it, but I didn't remember if I'd done it in class. Okay, so I h bar over 2m, and then you have psi star derivative with respect to psi of x minus blah, blah, blah. The key is, where did the integral go? There's no integral sign there.
Well, we're showing that we have limits of integration after running it to the same.
Well, my key is, we have the left-hand side of 1.26 is an integral. The right-hand side has limits, but doesn't have an integral anymore. It disappeared because we used used the fundamental theorem of calculus. The derivative of an integral has to be the function you started with. And so what we found in equation 1.25 was that our integrand is a derivative with respect to x times dx. So applying that fundamental theorem of calculus, you just have the integral is equal to the integrand with the limits applied. And then for a function to be normalizable, that is for you to be able to have it so it has a finite integral over all space, it has to be approaching 0 at plus and minus infinity. And hence that, when you put the limits in, is 0. And sadly, I actually went 2 minutes over and didn't do either of the problems I was going to do. We'll do some problems next class period. What do you say?
That's fine.
Okay.
For the part,
Go ahead.
we're going to be submitting that on E-Class then?
That's Moodle. No, on, yeah. We don't call it Bill anymore.
We call it E-Class.
Yeah. We now just call it Moodle. Anyway.
The same thing. And that's going to be...
No, it's on the OneNote. I sent you guys invitations to share on OneNote.
Okay, so you want it on OneNote?
Or, well, okay, maybe I misunderstood. My lecture is going to be, the slides are on OneNote.
And then homework when we...
Homework will be on eClass, yeah.
Okay. And that's once a week?
Yeah, once a week.
It's okay to call it Moodle because then we know it's you.
Yeah.
All right, see you guys.
All right, thank you.
Yep.
Next class period will be in the other room, but we'll see.
Okay,
We're going to do a test this afternoon.
so I'll just shut it down, Greg.